Welcome everyone. My name is Kristen Mulheron and welcome to the next webinar in GoProto's Office Hours series. Today we'll be talking about rapid injection tooling from design to inspection. Before we get started, I want to touch on a couple housekeeping items. You can make the slides a little bit bigger if you'd like by hovering your mouse over the middle of your screen and adjusting the slider to make the slides themselves bigger or smaller. You'll also notice as we go through this presentation that your questions that you submitted on your registration are listed on the slides throughout, but we do encourage you to participate in a live Q&A as well. There is the questions and answers box. It should be at the bottom of your screen, I believe. Go ahead and submit questions as we go through it, and we will try to answer them live. We do have quite a few questions or quite a few topics to go through today, so we'll probably only get to 1 or 2 questions per topic, but we'll do our best to get it to as many as we can. We'll not only be answering your questions live as we go, but it's intended as being more of a conversational format between the 2 speakers today. So with that in mind, let me introduce the 2 speakers. Today we have Jesse Lee. He's president of GoProto. Jesse's a 25-year student of the rapid manufacturing space. He's been a part of incredibly diverse product development programs, from early prototyping for products like the iMac in the 90s through high volume additive manufacturing for projects like HP's 580 color printers. Listening to client partner needs, utilizing the latest and greatest array of manufacturing technologies, and working with the best people in the product development and manufacturing community is what Jesse finds most exciting. Since the 1990s, Matt, the Vice President of Manufacturing here at GoProto, has been involved in guiding customers through rapid manufacturing, from customer service to printed parts, sheet metal and CNC, tooling and molded parts, always with a strong focus on the customer. With every project being important, he understands the customer needs and strives to achieve a great customer experience every time. Taking care of his customers, his teams, both domestic and international, and helping to ensure GoProto is the head of the industry pack is a passion that hasn't subsided for almost 3 decades. With that said, I'm going to hand it over to Jesse to do a brief overview on who is GoProto.
Excellent. Thank you very much, Kristen. Appreciate the introduction. And I wanted to thank you all attendees for attending today and making us part of your day to talk about rapid injection tooling. We're excited and grateful for your time. So GoProto is a group of industry professionals helping clients drive product development and manufacturing of custom prototype through production plastic and metal parts to ever quicker, more cost-effective and better results. Demands are always increasing. So our services span the continuum from initial ideation, as shown on the slide, through production and end-of-life manufacturing. So we're involved in every stage. Even though our company is called GoProto, we also do a lot of production work and higher quantity work. So wanted to point that out. We've been doing this line of work for a long time, so we have a lot of expertise in each of the processes that are lined out. So we're able to apply production knowledge to prototyping, and prototyping quick turn, high mix type knowledge into the production side of the equation. So that continuum allows us to really present a good slew of processes. So your product development is going to go from far left to far right. It's going to travel through various stages, and you will need guidance. You'll need some options for making parts that fit your needs, and then results you can depend on. And that's what we're here for. So we wanted to quickly go through the processes that we offer so that you kind of understand what we're talking about. And then we're going to be focusing specifically on injection mold tooling and molding, and then a little bit about 3D printing and additive manufacturing as well. So here we talk about concept models. This is in the ideation. So up on the top there, you see the ideation, prototyping, and production. So early ideation, concept models, we provide 3D printing and machined concept models that'll help you convey your design to your stakeholders. And then 3D printing, as we kind of move along, 3D printing certainly spans ideation, just early concept models into prototyping. So you're starting to build a few units. You may be sending them to your various stakeholders, maybe your assembly line, starting to kind of get into how is this thing actually going to work. And 3D printing, of course, is polymer as well as metal parts. Then urethane casting is an important technology that spans ideation through prototyping. Some companies use urethane castings for production, for things like skins on medical carts and larger parts. Automotive sometimes uses urethane castings. It's kind of an art form. Its applications have been shrinking a little over years as 3D printing gets better and injection molding gets faster, a little bit shrinking on either end, but it's still a very valuable resource that we utilize often to help customers through the ideation and prototyping stages into some production. Then CNC machining, a massive part of our business. We do a lot of machining in plastics and metals, again, kind of spanning, you see a little bit into ideation, certainly into prototyping, and then on into production. Quick turn capabilities with CNC machining, everything from 2, 3, and 5 axis machining. And then tooling and molding we'll be talking about today. And this is important because we are interested in doing the low volume, quick turn, rapid tools into the bridge realm and then into production as well. And that can be done by different types of tooling that we'll talk through, different types of tool materials, different construction methods in tools, and also just kind of your definition of what is prototype through production. But we wanted to make sure it's clear that you're going to have the same quality expectations all the way from beginning to end. So we focus very heavily on that. We're excited to talk about it more today. And then sheet metal, rapid prototype sheet metal all the way into production. Got a small little picture there of a part. We do 1Z, 2Z, small quantity sheet metal because a lot of plastic parts need to interface onto a sheet metal part. So it's a big part of our service offering. And again, that goes from ideation into prototyping and then on into production. Additive manufacturing is an important growth area for our company, and that is essentially using 3D printing for production. And so it's essentially a very similar process, but it is to 3D printing, but it is in higher quantity, often increased inspection, certainly continual improvement and monitoring of processes. So it's important to note that our expertise in injection molding and process controls there are spanned over into additive manufacturing, 3D printing to make it additive manufacturing. So we're able to utilize our knowledge there to provide you with the best possible options, possibly including 3D printing to make it additive manufacturing. And then of course, finishing, big part of our service offering that goes all the way from those ideation up through production. And that's gonna be painting, that's gonna be plating on the interior parts, things like brass inserts for secondary operations, any post-op machining, any of those kinds of secondary finishes to complete your product. We manage and we'll take care of for you so that you get ready to use parts. So that's a quick overview there. And then focusing in a little bit, we wanted to talk here about same kind of scale along the bottom, ideation all the way through production and obsolescence of spare parts. We're starting to focus in here a little bit more on injection molding and additive manufacturing. I want to talk about, several of you indicated that you wanted to talk a little bit about that today, hear a little bit more about 3D printing. Of course, we advertise that since we do both, we can help you with the blurred line that happens sometimes between 3D printing and injection molding, and sometimes it's unclear what to use when, and we can help you with this. So this chart kind of shows that on the tail on either end, you tend to use 3D printing because it's low quantity, it's often quick turn, you might have some changes, things like that are a little bit more difficult to do in injection molding. So we certainly understand that and can help you. And then as you move up through your product life cycle and or into higher quantities, you start to see that whole green area, it can be a question of whether you 3D print or injection mold. So it may be something where we quote it both ways. We talk to you about what you're trying to do on your project and possibly give you a couple of different routes or several different routes that you might go, help you with lists of pros and cons so that you can make your decisions. Or it may be something that you plan a 3D printing bridge production and then step into injection molding, where you see the yellow there. As you get into higher quantities, it often makes much more economic sense to get into injection molding. So we may help you with that blurry line, or you could also look at it as the green section, where it's not necessarily blurry, it's just that the processes might overlap, and we can help you through that process. And we're here to provide some guidance. So with that, Kristen, I believe we're going to get into the next slide.
Yeah, so this is just kind of a quick overview in terms of the questions that you all submitted today as part of your registration. We've taken your questions, and as I mentioned earlier, we've put them to essentially structure the slides that we're going to be talking through today. You'll see your questions along the sides, and the goal is for both Matt and Jesse to try to address those all along as we go through the various topics. As I mentioned before, though, feel free to submit some questions as we go. So with that said, we've broken all of your questions up into these 4 topics, and we'll be going through these today. The one thing that we did mention, Jesse touched on a little bit, is we will not be discussing the 3D printed tooling today, or 3D printing versus injection molding. We have done webinars on these before in the past, and those are on the resources page on goproto.com. And we also do have a couple comparison charts to give you a little bit more information on these topics as well at the same location. Jesse, did you have anything else to add on this?
Yeah, I guess just a little bit. You know, these are certainly things we do, 3D printing tooling, maybe 3D printing of some of the components. That's an important area that we are focusing on, and several of the questions were around that. At this point in the world, it is certainly a viable technology to 3D print parts of it. We generally are focusing as a business on very fast but predictable machining and EDMing of metal blocks to create your injection mold tooling. The reason is, like I just said, it's dependable, it is predictable, and it also is something that we can do extremely quickly and at low cost. So as 3D printing, as the technologies, we use it every day, as those technologies improve, surface finish is improving, tolerance is improving, and we can do some very complicated things with it that actually are quite simple if you use 3D printing. So it's something that we're constantly looking at deploying, but with the limited amount of time today, with just being an hour, and the other subjects that are so important to go over, we're going to limit our discussion on that today.
Great. So
Awesome.
as I mentioned, these are the 4 topics we'll be discussing today. They all revolve around metal tooling for plastic and elastomeric materials. We're going to start off with types of tooling. I believe, Matt, you are going to start with this one.
Yeah, thanks a lot. Thanks a lot for the introduction. Thanks everybody for joining us today too. We've broken down our tooling into 3 sections: rapid injection tooling, bridge tooling, production tooling. The differences being the rapid injection molding, mainly for open and shut type tools. Now, with that being said, we will put 1 or 2 undercut or hand load inserts into those tools as well. But anything beyond that, you're going to move out of that 1 to 3 week time frame, over into the 2 to 6 weeks in the bridge tooling. The nice thing about the rapid injection tooling is, a lot of times, these are just cores and cavities. They go into a house base. We can provide that cost savings to you from not doing the standalone mold base. So that's an advantage to do the rapid injection as well. The bridge tooling, that can also be done with just cores and cavities into a house base. But, you know, we got to look at the geometry and see how everything fits up. But really, the most important thing is people come to us for these processes. They're wanting parts. They're wanting parts, or wanting good quality parts. And is the rapid injection, the bridge tooling, and of course the production tooling will offer the same quality that you would expect. The materials that we use, mainly we use steel. For all our tools, we can use aluminum in the rapid injection, but really we found that over time we pay the same for steel as we do for aluminum, and why not use a better material? It allows us a little bit more options if changes need to be made, or adjustments of some sort need to be made for that. We do look at your design in all of our tooling processes, and we find that we don't want to change your design. You've spent your time working on this design. We want you to get what you've designed. So we will look at it, and we will use the slides and the lifters and the textures. I mean, we do what we can not to change anything, but to give you what you've been working on for the past several months. With that being said, Jesse, you have anything you want to add in here?
That's a great point, Matt. That whole idea that, you know, you've designed a part, you want it to be as you've designed. It often has important features in it that allow it to function like you want, and that's our mission is to make your part as much like you designed as possible. We may just optimize it to help you. Several of you asked about, say, cost and speed, and then of course one of the questions there, expected tool life. Sometimes design changes can affect those things, and so we may suggest them as a possibility, and then you can make your decision from there.
So one question's come in, Jesse,
Sure.
and Matt, maybe you could address how large of a part can be made with rapid and bridge tooling?
That's a great question. It really kind of depends on the design of the part, and the answer is that it's limited to the same principles as most injection molds. We've got upwards of a 2,000-ton press, and we can make parts quickly, or make molds quickly for that large of a mold. However, it usually takes a lot more machining, a lot more time, so it's going to tend to be kind of in the bridge tooling realm as a minimum, I would say. Matt, would you?
Yeah, I would agree. I mean, you get a larger part, it's obviously going to take more time. So I would say the larger parts move into that bridge tooling. Things that are, again, on the rapid injection tooling, where you're into that real quick hit of time, you want those to be, the 6x9.
Yeah, size of.
Yeah.
Size of your hand, kind of parts.
Size of your hand, and open and shut. That's where that fits. Not a whole lot of undercuts, not a whole lot of lifters or side actions or anything else needed. So that's what determines the rapid injection, and then moving into the bridge tooling.
Yep.
Great.
Yeah.
Moving on to the next topic. We have quite a bit to cover on the DFM, so we're going to speed through features here to get to that one.
Yep.
Jesse or Matt, did you want to go ahead and address this one?
Sure. Yeah, I'll get it started. Features that animation played pretty quickly there. What we want to talk about here is that we are making full feature injection molds. We are not compromising to say you can only do open and shut or straight pull, which means there are no undercuts. We wanted to show just a simple little graphic here that just shows that the yellow or orangish part is, or section is the part, and the blue part is what's called a lifter, and black is core or cavity, and then gray is core. And we're just showing that we make full feature molds. So when you design a part that's got, say, a hole in the side, or a clip, or a snap that's going to be fitting things together, holding a circuit board, you often are forced sometimes to cut that out to speed lead time. And what we're saying here is we should be able to do that for you, and we may be able to do it in the lead time and at the cost that you need. So it's good to know that we're full service, and we wanted to talk through that. Some of the questions that you all asked that are important are things like, what if I have asymmetrical part, which means something where it's not going to mold, the material's not going to flow evenly around the part. It may just be forced to one side. You've got thick or thin sections. How do you handle that? It's not going to be sometimes ideally designed, and we need to know, can you be adaptable enough to accommodate our sometimes tricky designs? And the answer is yes. We can employ different gating methods. We can employ slides and lifters, like we've said a couple of times, possibly different mold materials. We've got different runner systems that can help us with materials run or flow better. A lot of different tricks that we can employ to help you get your as designed part. And then how to design for undercuts and difficult features. What we're interpreting this for today's discussion, for the interest of time, is really how is that going to affect the mold design? And we're going to be using a case study today to kind of go through and talk about and show you the design for manufacturability feedback report that we provide, and then a mold flow if that's required, and then into the process flow of a project. So we'll be looking at kind of how we might feed back on, say, design. You might need to add a little draft. There might be things like that will allow us to make those features faster and better for you. And then an important thing that came up was texture. That is something we definitely can provide. We can do everything from mold tech to a custom texture to, hey, send us a part and we'll match it. We do acid etching. We definitely provide texture, which is basically just for anybody that doesn't know, texture is just a finish on a part that ends up making it have some features on it that say break light and make the parts look a little better. You've all seen textured injection molded parts, and that may affect draft, how much draft you need to have on the part. Draft is the angle that a part is designed with, so that as a mold opens, it's free to allow gas in behind the part and allow the mold to be opened and the part to be ejected. So that can draft and texture are very closely related, and we can help you through that process of knowing how much draft to add for different textures.
So quick question for you, Jesse, from the Q&A.
Yeah.
What's the difference between sliders and lifters?
Good question. So this picture here shows what's called a lifter, and then we've talked about slides. Slides are single directional action in a tool. So when a mold opens, it's generally opening in one direction, and a slide is an action in a tool, generally a metal pin, or which can either be actuated by the opening or by a electronic motor, and it just basically pulls a feature out of the way so that the slide can open, and that allows you to do to mold in something like a hole or a clip or some sort of joining feature. A lifter is what's shown in the blue here. And Kristen, can you possibly make that animation go again? Is that possible in this mode? Yeah, there we go. So a lifter is a two-directional slide. So it will go out to clear the feature and then pull down, in this case, in this image. So it clears and then pulls out of the way. So that involves a little bit more engineering. It's a little trickier, takes a little bit more time, can add a little bit more cost. So we try to avoid those for those reasons, but we certainly have the capability and all kinds of engineering knowledge to handle lifters. Hopefully that answers that question.
Moving on to design for manufacturability. We got quite a few questions on this topic, and so we have quite a few slides to go through here. Matt, did you want to go ahead and get started?
Yeah. Okay, for the DFM, here's some of the questions that we're going to address as we go through this process. Go ahead, let's get started, Kristen. So the DFM is going to start off with a page. It's going to have a picture of the part. It's going to have the other details. It's going to list the material, the shrink rate, the cavitation, the date. It's just a kind of a formal page for the document, and that's really all that entails. So these other slides as we go on won't be in any particular order, but they will all be included in the DFM analysis. We're going to take the part and we're going to look at the parting line. Parting line is where the core and the cavity, the two halves of the mold, come together and they form a line. You'll notice, you'll see it right there. That line is visible on the part. It's not terribly visible, but you will see it. And that parting line is outlined in red on the green part in the display here. Each one of these openings are going to be what we call a shutoff. That's where the core and the cavity will come together to shut off and form that opening. And then it goes around the perimeter of the part. One thing to note here, and we'll get into this a little bit more when we talk about draft, you see this parting line going across here, and then you've got the cavity labeled with the up arrow, the core labeled with the down arrow. When you're adding the draft to your part, you know, you want to know where your parting line is, and then add your draft accordingly. So you picture this part in the tool with the cavity pulling away, the core pulling away, I'm getting ahead of myself here, so let me get into the draft section and we'll come back to this. But the big thing was I want you to remember that graphic there.
It's important to note that, because you may have designed your part with a parting line in mind, and we want to show you where we think the parting line might be. And sometimes those are a little different. So like Matt said, we may need to kind of talk about draft and say, you know, on this surface, we're actually going to form that with the core. So you need to draft it the other way than you had planned. So there might be some discussion there. Yeah,
and that's another point to make. When when these DFMs come out, these are all open for discussion. You know, what we give you isn't cast in stone. If that doesn't work for you, let's talk about it and let's make it work. So now with the gate locations, we're going to show you how we're going to fill the tool. The gate is basically just that. It's a gate, it's an opening that the material flows through, and it goes into the void in the tool to form the part. And in this instance, with the size of this part and the geometry of the part, you'll see the node over there to the left that says Moldflow verified the gate location, which is pretty important. You'll see that a little bit later as well. All the material has to flow around all these openings and all these features and down through these narrow features to fill this part. So we want to make sure it's good. This is what was recommended. We verified it in the Moldflow, and it was all good.
Something real quick, Matt, that we a point of this DFM that we provide after the project is initiated and kicked off is that we provide these not only to show you that these where these features are, but to make sure that that's okay with you as well, that we're not, say, gating to a cosmetic location. Nobody wants a cover with a gate right in the front if you hadn't planned for it. So some of this is to show how we're going to construct the tool because we think it's going to flow well, but also to communicate back to you so that you say, yeah, that's an acceptable location. It's not going to interfere. It's not going to cause cosmetic problems, etc.
Yeah, that's a good point.
Hmm?
All right, ejector pins. These are pins that are strategically placed throughout the tool and to help lift the tool up and out of the mold, or lift the part up out of the mold. We have various sizes. You'll see the larger orange ones, the red ones that are a little smaller, the yellow ones get a little smaller yet, and the blue ones go out on these smaller features. That's not all we're limited to. You'll see over here, it shows how we're using the ejector blade, and that goes along this wall right here. You know, those features are so small we can't get a pin in there. So we'll match the blade up to the thickness of that feature, and it goes on the ejector plate, and it helps. This is a coordinated effort with all these pins and the blades and the whole ejector system. So with the proper draft and everything and proper ejection, your tool's going to run pretty smooth.
Matt, can you address, you know, we asked the question here, this is an example of in this DFM that we provide, there's a question there that would it be possible to add some material there to allow us to have that ejector blade? Why would we ask that question, and how does that affect the client there? How's the communication done?
You mean back and forth during the DFM?
Yeah. This is a possible lead time eater, and I just want to address that a little bit here that we may.
Okay. Well, typically the DFM is done on release. You know, once the project's released, the shop will sit down. They do the DFM. I present it typically the next day within 24 hours, and we get that to the client. Client reviews it. We have a review over the phone. We talk about any issues, or if, you know, I'm always open to compliments on the phone, like this is the greatest thing I've ever seen. So we'll proceed with that. But it does go back and forth, and there has been times where it goes 2 to 3 days. But the important thing is we don't cut any steel, or we don't do anything until this is agreed on. So you know exactly what you're going to get, you know exactly what we're going to do, and then we proceed to do it. But typically it's a 24 to 48 hour process. That's, you know, back and forth, and that's it.
Yep.
So quick question for you guys on the previous slide for gate locations. Just simple, what's the rule for gate locations?
What's the rule for it?
Yeah, this is one of the questions from the Q&A.
Sure, yeah. It there's a whole bunch of different possible variables that could affect gate locations. I mentioned already cosmetics, maybe interference. Sometimes different types of gates can leave different what are called vestiges, and you see here that the gate vestige is less than 0.3 of a millimeter in this case, but that might be too much. If you have a surface that is meeting directly against it, might not be good enough. It kind of, I guess the short answer is that it depends on the application of your part, the material we're using. We have what are called hot runner gates, which is what these ones are, which is the materials is heated through a manifold all the way down to where it touches the part, as Matt mentioned, or we have cold runners, which will leave some material on the part. They're a little bit more expensive, or the parts are a little bit more expensive, but the mold is less expensive. So there's a lot of different variables, and we have all of the options available to us, and so we can talk through the project with you and the part, and make a decision on what type of gate to use. I hope that's a
Yeah, and as Matt mentioned earlier as well, we're going to be talking through this Moldflow software a little bit later, and that to answer one of the other questions that popped up as well. We'll be coming to that in a few minutes.
Well, I
Sure.
do have
Matt?
something else to add on gating. It's always best to gate into a thick area on the part rather than a thin area.
Mm-hmm.
That allows that material to keep flowing in and not shut off, as you know, a thin area is going to cool off and close up sooner than the thicker area will. So always try to gate into a thick area of the part.
Yeah, good call. Okay, hopefully that answers it. We'll answer some more to that as we proceed through. Right now, we've moved on to a draft analysis slide. Matt, you want to continue on?
On the draft analysis in our DFM, ideally we like magenta and blue. That usually tells us that there's no issues on the draft. The green surfaces you see there highlighted, there either is no draft there or there is not enough, according to what our engineers see. So we'll identify these areas and come back to you and say, can we have another degree? Can we have 1.5 degrees on this surface here? You may tell us that for this surface here, we cannot have any draft. You know, so we have to deal with that, whether it's additional polish or somehow to prevent drag and the scuffing of the surface if there's no drag marks allowed here. So again, points of discussion. We'll ask for draft to make the tool run optimally. But again, it's got to fit your design. You know, you add draft to the walls, it's going to change the dimensions just a little bit. So, you know, we want to be respectful of that for your design. So we're going to point out, just like with all the other things in the DFM, we're going to point out what we see and potential issues, and then come to you and let you confirm them.
So I think on the next slide, Matt, it shows, oh, sorry, a few slides down, we have some feedback from the customer on exactly that issue. So,
yeah, this again is something that is typical in our DFM. We're going to look at the material thickness. We're going to look for inconsistent walls that could lead to potential sink issues. Sink is, you know, where the thick and thin sections might come together, and on the opposite side, it's going to pull that surface in. So sink is something that we're going to identify. Now, this particular part was an internal part, not saying that sink is acceptable, but you can get away with a lot more on internal parts rather than the visible parts. And when dealing with sink, it doesn't always require some sort of design change, because there's a lot of tricks in the processing, running the tool and creating the part, adjusting pressures, adjusting times that can help eliminate or minimize the sink issue.
Yeah, so here I think we had, this is an example of a question we had on this, or some kind of pointing out, like on the left there, you see we have an undercut feature, which is a feature that won't, when the tool opens, it's going to interfere with the steel opening, so, or the mold opening, so it would shear off that feature unless you have what we addressed earlier, a slider or lifter, which in this case is a piece of steel that we machined, that we manually place into the tool when it's empty, and then the mold closes and the material is shot around it, and then when the tool opens and it ejects, that piece of steel comes off with the part, and then we manually pull it off. So it says it's released with hand-loaded insert, which we wanted to clarify there. We'd probably make 2 or 3 sets so that we can continue the cycle quickly, but that may be an example of, say, where the draft would be different than what it would be if it was formed with the core or cavity, so we want to communicate that. And then on the right, we talk about that, that we might want to change the draft here. This feature can be made with a 2-sided shutoff. Matt said earlier, those shutoff is where the steel meets together and then doesn't allow plastic to form. So 2-sided just means it's on 2 sides. So we're just indicating that the draft is going to be different there than it will be, say, on the part that's, or the feature that's on the opposite side of the part. So we just want to make sure and clarify that so that the customer understands what's going to be done in that area. And then here, this is just like Matt was talking about earlier, where we said, hey, we'd like to have some draft in this area. Would it be possible to add 1 degree? Again, draft is just an angle that's designed into the part to allow it to eject when the mold opens. And if you don't have draft, then when the mold opens, all it does is just simply scrape along the plastic part, and sometimes that can leave scuffing. And here the customer said they determined that it was more important that they have no draft on that surface than to have a couple little, like, essentially drag marks that go along the part. That was going to be acceptable because, as Matt said, it's an internal part, and they needed that feature to have no draft so that it would fit with the really tight-fitting electronic assembly that was in there. So just an example of how we'd communicate the question, get feedback, make sure everything's good before we proceed. And then here, question, we were talking about these tall features and the fact that, as Matt showed earlier, the part is fairly thick up at the top up there. And so as the part cools down there and is ejected from the mold, there might be a tendency for those 2 tall features to kind of draw inward. And we decided that it was important, and we worked with the customer to take the next step that's available, and that is to go into the mold flow software, which we'll show later, which showed that area might have some warpage. Wanted to indicate to the customer that's a concern. Customer replied back in yellow saying that's going to be okay as long as it's within the specs, and we've got them fairly loose for those features on the drawing. So we communicated the issue. Customer said, yeah, it's going to be all right. It turned out to be great, as you'll see in the final parts pictures and the inspection report.
So related to some earlier, the earlier slides on draft, we just have a question that came in on, do you prefer to receive CAD with estimated draft already applied, or is it easier to leave the models undrafted and let you specify draft surfaces and amount of draft required?
Great question. Matt?
Yeah, I prefer to get the models drafted. I think that helps everybody. I think it helps the customer from the standpoint of, if there's an assembly, they're putting together in their assembly on the tube drafted model, so they know it's going to fit. You know, then if we have to tweak it, you're only talking thousandths of an inch if we have to increase the draft for some reason. So I prefer to get the models with the draft, and we can go from there. And I'll just put this into for everybody. If you've got prints, send the prints with a 3D. So we'll take it all.
And on related topic, or same topic, can zero draft affect dimensional tolerance?
Yes. Yeah, absolutely. It can. As zero draft just means that there's no draft, no angles at all. So when the tool's ejected, I mentioned in the slide before that it can create some scuff marks. It also can sometimes, if you, let's say, have a circle, a hole feature, and it has zero draft and it shrinks around the core pin that makes that, and then you pull it, it can actually cause that hole to sort of pucker or to change shape as it pulls out. It can create kind of like a crater type of thing. It can definitely affect the tolerance on certain features. So that's just one example. The short answer is yes, it can affect dimensions. I think.
All right, moving on to the next second half of this, the DFM analysis is the mold flow analysis. Jesse, did you want to go ahead and start on this one?
Sure. Yeah, mold flow is an available available service that we offer. It's actual Moldflow software. It is an additional cost process that usually through the DFM we can determine, and through customer specifications and exactly what the application is, if a Moldflow is required. We have enough experience that we can often, put that knowledge into play along with that initial DFM and say this part is safe enough that you don't really need to run a Moldflow. It's going to be fine as is. Sometimes it's a little unsure. We're not quite sure, and or the customer wants it for their future process, or at least to put in their project folders and show that this was completed. So in this case, we did run a Moldflow, ran it through the software, and you'll see as we go into the next slide, we start. Moldflow is a simulator software that allows us to simulate what is going to happen as a mold is filled and the part is ejected. And so we start off with these process parameters, which is important to note. We're going to be open with our process parameters, which is important. If you plan on using GoProto for an initial trial tool, maybe a bridge tool, and then go into a high volume production tool, say with a contract manufacturer further, we're going to be open with what our process parameters were so that we can learn from this, so that when we're providing you great quality parts, everything is good, and then you're taking that next step, that we can help transfer that. So we can help you with, again, that design continuum. So we input our process parameters here, and then Kristen, next slide. This is a little animation that just shows the flow of the material as it's injected into the part. So those two towers are the gates that Matt mentioned. They're hot drops. The material is flowing into them and then out into the rest of the part. That's what that blue front is. You want to see that there's fairly low stress. You don't want to see a lot of red. You want to see that things are able to flow nice and evenly so that they don't build stress into the part. So this is an important thing to say. Yeah, we've got a pretty good confidence of fill. Things are flowing in a nice equal way. You don't have a big area of stress. So this is kind of a validation of where we put those gates to answer that earlier question. And then next slide. We go through, there's just kind of a series of things we're looking for. So we look at that, how it's going to flow, volumetric shrinkage, like Matt mentioned, we want to see a consistent, even shrinkage. That just, when you inject a part that's molten, it is warm and it's molten. So as it solidifies, cools down, it's going to shrink back down. And we want to make sure that that is happening evenly, that there aren't any areas that have got big warning signs, generally in red. Here you see there are a couple of those little thick clip spots where it's going to shrink a little bit more because they're thicker. And so that may cause a little dimple in the backside you can see there, or possibly pull them out of tolerance. So it's kind of something to be aware of, is what that color tends to indicate. But in general, this part looks pretty good with shrinkage. Next slide. Then weld lines, these are flow fronts. The material is flowing from those gates that we showed 2-3 slides ago, and it's flowing out around any obstructions, i.e. holes in this case, and flowing back around like a stone in the river. You know, the water separates around the stone and then comes back together on the backside. And or like hot lava, you consider, and then it's getting cool. And as it comes back together, it needs to knit back together. And you'll always see a knit line around an opening. And the hope is that it's doing so, or that it's knitting together while it's still warm, so that you have, this is showing the degrees of reassociation between the two fronts. And hopefully you see low degrees so that it's a nice, flat, minimally intrusive knit line, and again, or weld line. And again, this is to show that we don't have any areas that possibly could be weak or cause a cosmetic problem or have a dimensional issue. So just a quick check. This one looks pretty good because we don't have any major red areas. All right, and then sink marks, Matt mentioned earlier, there's some thick sections, and this just shows areas that might have sinks. So this could be a cosmetic issue. This could also, someone asked earlier about draft causing issues. Sink can sometimes cause dimensional issues because the part might sink a little bit, might cause a feature to kind of lean over. I always think of the Leaning Tower of Pisa. You know, it's on softer ground and it leans over, and that's a big boss, and that thing's not in tolerance anymore. Same thing can happen with molten injection or molten plastic as it's injected. So we want to check and make sure that there aren't any areas that are glaring red, and this one looks pretty good. Overall warpage distribution, this shows that generally we're in pretty good shape. Interest of time, we can skip quickly, Kristen, on this one. And then just quick conclusion. So just, hey, we ran it through. The simulator is another point of data that we need to look at. And overall, it shows that maximum pressure is within realm. packing condition is good. You know, kind of go through each of these steps to say, generally we're in pretty good shape. As we mentioned earlier, there's some deformation that we're a little concerned about, so we wanted to make sure that that's known, so then we can agree and keep our eyes on it, but it should be okay as long as we're within spec. So this mold flow combined with our initial DFM and then our engineering knowledge and processing knowledge allows us to determine if this should be good to go or not, and make recommendations accordingly.
So moving on to the last topic here, we have the process and workflow. These are the questions that were submitted from the registration. And Jesse, do you want to go ahead and start with this one?
Sure, yeah, Matt, I can both do these next few slides. So this is once we agree on those processes, like Matt said, that those previous processes are anywhere from, sometimes we can do it before the kickoff. If it's a rush project, sometimes it takes 2 to 3 days. Once the project is started, POs received, get started. And then once that's agreed, sign off, we're good, then we start constructing the mold. We'll actually start ordering and cutting steel. We'll provide feedback on schedule, which we'll show in the next slide. And then looking through the questions, what's the overview of your process? What should we expect? We're going to talk through that here a little bit. What lead time can we expect for a first article? That's the holy grail. Everybody, we want our parts back as fast as possible. And the answer to that is it's going to depend on the type of tool you created or that you've ordered, the complexity of the part. Our lead times generally span anywhere from a week to, on the outside for a production tool, multi-cavity and so on, is on the 8-week range. But we see a lot of 2 to 4 week is kind of a typical lead time for us, and we're very interested in those quick turn, low quantity, but highly precise parts. And then what can we expect from our first article inspection? Great question. We do first article inspections. We do it on every project. We'll show you at the end of the presentation here what an inspection report from us looks like. Let's go to that next slide. So this is the Gantt chart that is the progress report, and this is something we provide weekly throughout the course of the mold construction. On the left, the third column over, those are each of the processes that we go through in constructing your mold. Then as you go over to the right, you see the arrows and the that are at the corresponding dates up in the calendar that show what days we're going to be constructing or doing each of those processes. We also want to plan for and show things like holidays, Easter in this case. And then at the right, you see the little red squares there. That is first article or T1. Also possibly T2, which is if there are changes need to be run again. You know, so we have those planned dates. So beginning on the left, end on the right, so that you can see the whole project. At the beginning of the project, your mold components are chunks of steel. They don't really represent a very well understood progress in your tool. As soon as we get into recognizable things, generally within a week or so, we'll start to include pictures so that you see exactly where we are, exactly what process we're in, so that you can report back to your stakeholders so everyone knows exactly what's going on. Also, just highlight in the yellow box here, sometimes there are things that take a little bit longer than we'd planned, and we'll put a correct, an action plan on what's going on here. In this case, we say we've got a little bit more EDM work to do, and we're putting on another shift, and we'll it shouldn't cause any problems. So we try to be proactive in our communication to show you where we are, if there are any things that we've noticed, what we're doing to get them fixed so that you can rest easy. Next slide. This is the inspection report, and we're nearing the end here. So just quickly, this is a drawing provided by a client that shows in the upper left the notes, things that need to be paid attention to. In this case, material, surface finish, no regrind, and so on. And then the dimensions that are critical, that are called out by the customer. We circled the dimensions in red to show those are the dimensions that we're going to be measuring, and then we'll be reporting on, which in the next slide here, this is a typical inspection report. This shows the part parameters up at the top. Then note 1, 2, and 3 shows those are directly from the drawing, and then we show that we've checked them. So those are all okay. And then the inspection report here, the dimensional inspection report, is very important. And we actually wanted to show one here that has some issues that are kind of alerts, because often as you make a part, make the tool, shoot the parts, no mold is perfect. There's always a question of some dimensions might be a little bit out. We've all got physics to deal with. Sometimes there's a little bit of challenge here, or something mold's a little bit unexpected. Sometimes we want to say, yeah, this is an alert, and then we put a remark on what's going to happen with it. Either it's something, yeah, we recognize that there's an issue here, we're going to fix that, or sometimes it's something that, hey, this is very close, so it's an alert. We may want to talk to you about, is this going to be critical? or is it something that can be adjusted and we can work through it, and whether it be adjusted on the drawing, or needs to be, yeah, in fact, this needs to be adjusted in the tool, and we'll quickly get through this. That's very important because this is a stage that a lot of time can be lost if your molder isn't all over these sorts of results. If you just get parts in and they're out of tolerance and you don't know why, you haven't received an inspection report, your assembly isn't working, you want to know what's the problem so you can fix it. And we want to avoid that whole line of questioning. You see exactly what's going on, exactly what to expect from our parts, so that you can proceed quickly through your next steps of the project. And then also our corrective action if there are issues.
So Jesse, a question in from the audience is, what tools do you use for inspection? CMM, CT scan, et cetera?
Yes, it depends again on the type of feature. There's a lot of different tools we use. On CMM, yes, of course. Sometimes scanning, so digital scanning that can allow us to compare the part to the CAD file, and sometimes that's a stoplight type of thing where you have the green, yellow, red. There's also, of course, hand tools. Calipers sometimes are the cheapest, fastest, and sometimes the most accurate. You see that on this report, we over on the right next to the yellow, the last column, it says inspection tool, and you see CMM, caliper, CMM. So we will show what tool we used to inspect it. That is an important note because sometimes you're going to have incoming quality control. So sometimes your own in-house quality control is going to verify our results, and we want to see that we're using the same tool. Or you may, as I mentioned earlier, you may be going into a high volume production tool of some kind later, and you want to see that you're going to be measuring it the same way. We will also look at the drawing, the slide before, and if you have a high tolerance area, we may want to discuss that. We are going to have an inspection plan to make sure that we can inspect like you expect, and that may involve some negotiation on what type of tool and how we're going to set the thing up and how we're going to fixture it to hold it so that we can measure it.
Another question on the topic is, do you perform FAI for 100% dimensions on drawing?
Yeah, this is an FAI, that stands for first article inspection. So yes, we provide it. 100% depends on the part. 100% dimensions is often difficult to do because most parts are defined by thousands of dimensions, and so that can be long and expensive. Generally, there's some critical to function or CTF dimensions that we inspect to. And again, that can be negotiation. If you require 100% on all the dimensions that you lay out, we certainly can do that. Sometimes it requires a little bit more than what we've budgeted in, so we'd have to have just some nominal fee added, but we can do it. Also, it depends on the quantity of parts that you're running. Sometimes if you're running thousands of parts, doing 100% inspection just isn't really feasible. So there's often a quality plan, a CPK kind of thing, where we may choose a few, do some statistical analysis on it, and recognize or then see the results that it's good enough that all the rest of the dimensions on the part should be acceptable. So it kind of depends on the program. Matt, would you?
Yeah, that's correct. I mean, if the customer requires 100% inspection, we'll do it. But again, it's the quantity of parts, and then we can talk about that.
Mm-hmm. Time involved. Okay, and then up again comes the tooling progress report here, just to show that sometimes after T1, there are often, as I showed on that last inspection report, sometimes there are issues that come up, whether they're parts or dimensions or material, surface finish, something like that, that require a spin on the tool, quick fix of it, and then a reshot of parts. Or sometimes you, at that point, get your first articles in and you realize, oh, I made a design error and I need to make some modifications, or I want to add a feature. Then we can go in and quickly get that tool modified and then go back through what's called T2 or second articles and repeat that cycle. We try to make that as fast as possible. Again, this is an area that a lot of time can be lost. If you get first articles in, you have a whole bunch of stakeholders you gotta work through. Sometimes this can take a long time, and we will stay on top of this with you. And it's important to note that we'll have good control of it so that we don't lose that valuable time.
Another question on the validation topic is, can you perform full validation, IQ, OQ, PQ?
Yes. Yeah, absolutely. Again, that kind of depends on the type of tool that we're looking at creating. So full validation is just to go through the process to show that we're going to we have a process that is consistent in its results over time. That's what that means for everyone who might not understand that. And if we're making a quick as Matt said, that as we looked at those different types of tooling, a quick tool that's made 1 to 3 weeks, I just need something quick that represents my drawings, that's in the right material. It may not be required to do that full validation process. But if you're stepping into bridge or production tooling, maybe multi-cavity, you want to make sure the different cavities are producing parts that are the same, then yes, we'd step into those next levels of inspection and analysis. And yes, we can definitely do that. Sometimes they are additional cost, and or we need to plan for additional lead time, because sometimes those do take a couple to a few extra days depending on the process required.
Great. So we have quite a few questions. We're not going to get through all of them, but I'm going to try to focus on some of the more general questions. Do you provide these tooling services for a project that is just producing a tool for use by a third-party molder, or are these services only available if you do molding as well?
Great question. We do both. Those are called for export tools. We do sometimes make a tool, run the parts, qualify them, make sure they're good, maybe run you some pilot production quantity, and then ship the tool to a production molder. Yes, we definitely do that. Or we do it designed to run in-house. There's a little bit different cost structure. It's a little different types of inspection, maybe components that are on the mold if it's designed to run on our machines versus someone else. Certainly a little bit more communication with design, mold design up front. If you're going to be planning to run it at another shop, we need to make sure that the connectors are the same, and that the sprue, which is where the gate runs in, is all the same. So we need to communicate that a little bit more. So might be a little bit more time. It is a little bit additional cost to have a or export mold for that reason too.
Question on materials. And just before we even get to that question, I want to point out that we will be discussing materials in the next webinar as well. So hold tight for that one. It'll be the end of October, early November. But in the meantime, one question came up. Do you do rapid prototype injection tools for liquid silicon rubber parts?
Yes. Yeah, that's actually come up recently. Silicone is a kind of a scarce material at the time because of COVID. And yes, we do. We're doing several projects in it right now. So yes, absolutely. Was that the full question? Is just, do you do, oh, and I guess just materials in general. Yes, we didn't really talk over that today, but we do offer material selection. We do run custom materials. We have a full variety of all kinds of different plastics. We can run materials that you have. If you have a pre-colored material, you can send us some to run a prototype or bridge tool that we can run your plastic, or order it directly from the material manufacturer. So huge range of materials available.
How about medical grade materials?
Yeah, absolutely. A big part of our work is medical products, and yes, we do medical grade. We do not run clean room, so our process is not set up for clean room for medical, but we do medical components is a huge part of our business. We understand how to validate that, and also something important there is material certificates of conformance and compliance. We can provide all of the documentation on the material that we purchased and or acquired and then used in the parts.
Great. Well, so we have, like I said, we have quite a few more questions, but what we're going to do is we'll take all these down, and we will address them one by one after. In the meantime, we also have, these are the contact information. You can send any questions you have to quotes@goproto.com, and we'll forward that on to whoever the most appropriate person is to answer that. Jesse, any parting words?
I really appreciate everyone's time. Matt, great talking to you. Thanks for joining on, Kristen. I appreciate it very much, and all the attendees. This is a diverse group. We had a lot. Each of these subjects could be, weeks-long courses, and we want to acknowledge that we didn't get to everything, but we will follow up with you to make sure that your individual questions were answered. We're here to help. Thank you very much for your time.